It's always interesting to do this rapid transition. We're happy that you've rejoined us. We've had a great morning wind up here. We're ready now for really a deep dive into some technical issues. We're fortunate to have our speaker with us today, Mr. Russinovich, who just flew in from London, where he was obviously involved in some good Microsoft business there. We are interested in, as well, in his perspectives as we go from what we heard, the primarily service-oriented solutions that are adding lethality, now to an opportunity to look at one of our prime vendors, one of our strategic partners, and that is Microsoft. We are, in fact, going to have a chance to listen and hear. We started a little late, but I think we've got plenty of time still to get into our presentation. We have with us again Mr. Russinovich. He has been in Microsoft for a long time. He is, it's kind of an interesting path he's taken. Perhaps he'll touch on it. His PhD is from Carnegie Mellon. He is the Chief Technology Officer of Microsoft Azure. Really, we all know Microsoft Azure is a global enterprise cloud platform. In '96, he co-founded Winternell's software and developed a suite of Windows administrative and diagnostic tools. He's remained with Microsoft since Winternell's was acquired in 2006. He's a writer, has published a number of texts, but he's also published a number of Microsoft manuals important for the operation of this variety of systems. So he's known inside the corporation, inside, frankly, Business America, but as well popular techno thrillers. I love the titles here of, you can imagine the cyber threat and the cyber attack books, Zero Day, Trojan Horse, Rogue Code. It sounds like a hit list of software or malware that you might imagine. He's got a perspective on small business, startups, large business, and problems. He's going to address it for us machine learning, repurposing machine learning algorithms from different domains for the purpose of cloud defense, and I imagine much more. Ladies and gentlemen, please welcome to the stage Mr. Russinovich, our guest speaker.
Thanks. Good morning, everybody. So what I got for you this morning is a little look at the way that we're applying machine learning for the purposes of cybersecurity across Microsoft. And I've got some case studies I think you'll find interesting and really highlight the kind of out-of-the-box thinking that we're using for how to apply machine learning to help secure our systems in a better way. So one of the benefits of working at a company like Microsoft is that we've got dozens, hundreds of cloud services, including ones that you're familiar with, like Xbox Live, to Office 365, to many of the platform services that we run as part of our Azure cloud platform. You can see that we've got things like Cortana, SQL Server as an on-premises product. We've got Windows Defender, advanced threat protection that runs on millions of desktops around the world. And this gives us the benefit of collecting enormous amounts of data. It also gives us the benefit of developing cyber defense systems or solutions that can be applied across a bunch of different products and services and domains. Now, if you take a look at the kind of scale that we're operating at across those services, I think this gives you some insight into the amount of data that we have at our disposal. And of course, anybody familiar with machine learning knows that machine learning is fueled by data. We've got, on a daily basis, 500 million active Microsoft account users. We have 18 billion authentications a day through Azure Active Directory, our identity system, across tens of millions of organizations. We've got a defense system as part of Azure Active Directory called Identity Protection that uses machine learning to identify anomalous logons, and the obvious ones being somebody logs in DC today and then logs in from Beijing tomorrow, or a few hours from now, rather, an impossible transit kind of authentication. We detect 30 million of those a day based off of looking at individual organizations with logon patterns with machine learning. We deflect 1.5 million compromise attempts a day, and we detect 77 million threats across devices that we have our cyber defense or cybersecurity solutions installed on. But when we take a look at machine learning, there's some enormous challenges or significant challenges in getting a machine learning solution from concept into production. If you take a look at the standard process for developing machine learning algorithm, you have to choose the learning task, define your input, clean the input, apply data transforms on it, choose your running options, choose what the output is, choose the learner itself, the machine learning model, go view the results, debug and visualize where there's problems, maybe you've got dirty data you need to clean up, analyze and see how accurate the predictions are coming out of that model. And this is a very iterative process. If anybody that's worked in machine learning knows that it's pretty ad hoc today, and it's pretty experimental and as much an art as a science. And so it takes many attempts to refine, pick different models, pick different inputs, and finally come up with something that is proving effective at predicting outcomes. And then once you're ready to take that solution and put it into production, you've got a variety of different people that have to be applied to the domain that it's going to be applied to, from security experts that can assess the landscape and determine where it's best applied, the machine learning experts that I've already talked about, product managers that will define the requirements for the ultimate solution, how end users are going to interact with it, how the operators are going to interact with it, the engineers have to develop it, the operations engineers, if it's an online solution, have to make sure it's running with efficiency and reliability. And then finally, through it all, compliance and privacy have to be taken care of. So it's a pretty expensive process from conception to production. And what we've done at Microsoft is ask ourselves the question, can we accelerate the deployment of machine learning solutions by taking our learnings from one domain where we've applied it and taking it to another one? So saving as much time and energy as possible by reusing different components of the pipeline, different processes. And I've got, like I said, a few examples where we've done that successfully that I think show the kind of innovative approach that can be applied, taking a solution from one domain to another one. In machine learning, if you're familiar with it, there's a way of developing machine learning models called transfer learning. And if you take a look at traditional machine learning, you take one different machine learning task or predictive model, predictive problem, develop a learning system, which is the machine learning model that you would then deploy. And with traditional approach, you would develop a different learning system for each specific problem. With transfer learning, you take the learner that you develop from one domain and then you apply it to a different domain. So as one example, if you've got a visual object recognition model that knows how to distinguish cats and dogs, you can take that into a different domain with custom data sets, leveraging that learning that was done on that particular data set for that particular domain and apply it to another one, like faulty parts in a factory automation floor. If you take a look at the different types of machine learning that are in use, in fact, it's strongly believed that transfer learning is going to be what drives the richness of machine learning in production cases. The different types of machine learning include reinforcement learning, where the machine learning model learns on its own based off of feedback that it gets itself. There's unsupervised learning, where the machine learning model is there trying to solve problems and predict them, again, taking feedback from those predictions. And then supervised learning, the most classical form, which is I take data, I label it, what's good, what's bad, and then train the model to predict on new inputs what's good and what's bad based off of that labeled data that was fed to train it. Transfer learning offers the opportunity to leverage all of these types of models, all of these other types of learnings to produce new solutions. So the first case study I've got to share with you is one where we looked at protecting our customers and ourselves in Azure's infrastructure. As a cloud platform, we've got a service called virtual machines, where customers can come and within a minute or two deploy a virtual machine of Windows or Linux, connect it to a network, maybe a private network, and sometimes a public network. And the challenge we've got is that sometimes those machines become compromised. They get infected from an insider, they get infected from a breach from the outside because they've been poorly configured, or there's a vulnerability that they're exposing that an attacker takes advantage of. Our goal is to try to identify those compromised virtual machines. If they're our own, we want to go investigate and mitigate them. If they're customers, we'd like to let them know that we suspect that one of their virtual machines has been compromised. Now, when you take a look at how you would detect a compromised virtual machine, one of the ways is just to look at its network traffic. If it's suspicious network traffic, then that can be an indicator that it's been compromised. But how do you determine something suspicious? What we've run into previously is that when looking at network traffic, we had no one model to identify a potentially compromised virtual machine. Every single network protocol has different characteristics, different behaviors. So an HTTP server would have a different kind of set of behaviors, connecting to different clients, serving different kinds of data, having different durations of connection from an SMB server, a file server connection. And we saw this kind of as an intractable problem. There's literally thousands of different protocols that are served off of the virtual machines. And so we didn't feel that it was tractable to go down and develop a separate machine learning model for each and every one of those. It just wouldn't scale. So our hypothesis was that we could create a generic machine learning algorithm that would be applicable to any protocol and identify suspicious or anomalous behavior. And what we decided to investigate was something called ensemble tree learning and develop an algorithm that would be generic across all protocols based off of our learnings from other places inside of Microsoft. We use ensemble tree learning, something I'll describe in a minute, in a few different domains at the company. One of them is with our Connect service. If you're familiar with Xbox and Connect, the product that came out about 10 years ago, that was one that you had cameras and depth sensors that would detect your motions in front of the Xbox. The other place that we've applied this is in Microsoft Research to identify tumors in CT scans. And what ensemble tree learning is, it's an algorithm that takes inputs and then classifies them and comes up through a decision tree with a positive or negative based off of whatever prediction you're looking for. In the case of the virtual machines, the kinds of data we can feed into the model to train it are what we call IP fixed data. IP fixed data are the network flows and connections data that we collect off our telemetry that's monitoring the infrastructure itself underneath those virtual machines. So we don't have to have the customer do anything explicit with those virtual machines. That's one of the benefits of the cloud platform is that everything's API driven. We've got a software-defined networking stack that's homogeneous across the millions of virtual machines we have in operation. And so we can collect this data and then feed that into a machine learning model. We need to label the data somehow, though. We need to know what is a suspicious or malicious IP flow, IP fixed set of data, and what is a benign one. And so, again, another benefit of being at Microsoft is we have a tremendous number of inputs of labeled data. You can see some of them here, like third-party threat intelligence feeds that will tell us specific IP addresses out on the internet are compromised or malicious. Our Cyber Defense Operations Center, which is looking ourselves and performing investigations and identifying compromised virtual machines. And then we can look at the telemetry of the network traffic coming off of those. Our Threat Intelligence Center, Microsoft Security Research Center. And then we also have red team activities that we can go look at. And those are labeled data because we know that a red team activity is malicious by definition. Now, what we can extract from those different flows are a set of data like what the rate of connections are going outbound or inbound from a particular IP address. We can look at the number of different connections that are made over the course of an hour. We can look at the duration of those connections. We can look at the rarity of the ports that are being connected. So there's some ports that are much more heavily used on the network than others, like port 80, of course, or port 88. And there's ones that are very infrequently used. And so all of this data can be fed in to a machine learning model that can then take a look, based off of the malicious flows and the benign flows, come up with a profile of what is potentially malicious activity. For the tree learning algorithms, we took an approach called ensemble tree learning, which is to come up with the set of input data that you can see there. We've got N examples and M features, the features being the IP address flows, the connections per hour, and so on. The number of samples that we've got are the training set of data that's labeled, so all of the different types of IP flows, IP fixed data sets, and whether they're benign or malignant. And we create subsets of those through something called random sampling with replacement, meaning, and what that means is that for each random sample, we start fresh with the whole data set and then just randomly pick a subset of the inputs and then train the tree decision algorithm on that subset of data. So just to give you an idea of what one of these decision trees looks like, if we start with the feature that is most likely to separate the benign from the malignant in the case of the sample data set, like rare port flows. If the rare port flows are above some threshold or below some threshold, we might take one branch or the other in the decision tree. For example, if the rare port flows is below a threshold, then we'll take a look at the next feature, which is number of outgoing SYN connections or TCP/IP connections. If that's below a certain threshold, we'll take the left branch. If it's above a certain threshold, that might map to a malicious, likely malicious activity, and we'd classify it as malicious there in that red box. Otherwise, we'd go down and take a look at one of the other features in the number of incoming flows, and based off of the thresholds there that have been trained as malicious or benignant, we'd come up with another prediction as to whether it's a malicious or benign flow. And what we do, like I said, is take the random subsets multiple times and train the decision tree based off of the features extracted from that random subset. And then what we do is essentially have a vote. So when we test, we take the majority vote of those decision trees that were individually tested off of a new flow and then come up with a prediction. Is it malicious activity? And what we did was deploy this into production and look at the effectiveness of this approach. The amount of data that we're training for these decision trees, we do this regularly because traffic patterns change over time. And so you can't deploy a machine learning algorithm and not expect it to decay, which is what happens if you don't feed it fresh data that represents the changing environment, is that we've got about 3 gigabytes of data that we train the model with per day. That represents communication with about 5 million IP addresses off the data set that we're training it with. And the training takes literally just a few seconds. Decision trees, one of the benefits of it is that it's highly parallelizable. And so you can train all those decision trees at the same time. And so have very quick throughput, low latency on the training. And then what we do is, as we collect IP fixed data off our systems, we run classification several times a day to determine whether something's potentially malicious. You can see that the non-ensemble learning approach that we'd taken earlier for just a subset of the different data flows had a true positive rate of about 82% with a very low false positive rate of 0.06%. We wouldn't want to deploy something into production that had anything other than more significant true positive rate without significantly increasing the false positive rate. Of course, the false positive rate going up means more spurious notifications to users that they have to go waste time responding to. And you can see in this case, the approach proved to be very effective. We raised the true positive rate by 3% up to 85% without affecting the false positive rate. Now, if you might be looking at that and saying, wait a minute, 82%, 85%, that's pretty close, what's the big deal? But when you're talking about millions and millions and millions, tens of millions, hundreds of millions of network connections per day, that 3% adds up to a lot of malicious activity that we're now detecting that we weren't detecting before. And as everybody knows, when it comes to cybersecurity and defense, keeping one bad guy out could be the difference between a disaster and continuing smooth operation. You can see the kind of notification here. There's a screenshot that we would show a customer that the algorithm fires on to determine or to suspect that there's a malicious activity, saying, hey, looks like you've got suspicious activity on this virtual machine. Threat level's medium. We would tell them what port flow, what time the malicious activity was detected, and then they could go follow up with investigating themselves. And this is presented right inside of Azure Security Center. Now, as a bonus, this kind of monitoring with these algorithms can detect attacks before they even happen. This is another example of the benefit of working in a cloud platform where we've got millions of customers deploying virtual machines and workloads. There was a MongoDB vulnerability that was exposed a little over a year ago, identified a little over a year ago, where MongoDB databases, this NoSQL database, where many people were putting them openly on the internet without any kind of authentication in front of them, which meant that an attacker, if they discovered the presence of a MongoDB database on the internet by looking at a machine and seeing if port 2717 was open, could gain administrative access to that database. And what attackers did when they discovered this was go searching the internet for these open MongoDB databases, gain control of them, and then encrypt the data in those databases and replace the data with files that said, hey, your data's been encrypted. If you want it unencrypted, go pay this amount to this cyber currency, and you'll get your data back. A classic case of ransomware. When we took a look after we came up with these algorithms and applied it historically to the data we collected, we could see the attack before it happened. You can see that spike there in the number of detected suspicious MongoDB scans, as determined by that ensemble tree learning algorithm, spiked right before the vulnerability became public and the attack became public. You can see the article headline there. And then we saw a little bit later, a few days later, another spike, likely due to copycat attacks after many of the ports were shut down. Many of the databases were locked down. Some of them were not, and then we saw a second phase wave of attack as some other people looking at it and saying, hey, opportunistically, maybe I can take advantage of this too, started to scan for open MongoDB ports. Another place where we looked back historically and saw an attack before it happened and actually could see the phases of the attacks, in this case because there were several, was WannaCry, the cyber attack that we attribute to the North Koreans that attacked SMB, a vulnerability in the SMB 1.0 protocol of Windows. You can see up to that blue line there, basically a low-level noise of scans that the algorithm reported as suspicious of SMB ports. And then you can see that we released the patch once we were notified of the vulnerability, and we saw an slight increase in activity as security researchers reverse engineered immediately the patch and figured out how to attack vulnerable SMB ports. And so they started scanning the network, looking and seeing which ones were vulnerable. Then we saw Metasploit release a plugin that would also test for this vulnerability. And so we saw another rise in attacks. And then finally, we saw the leak of the Shadow Broker actual exploit. And then we saw that, as it started to make its rounds, another wave of attacks. And this is across the whole sample set of virtual machines we've got running inside of Microsoft Azure. Again, this is historical, but the next type of this attack we will see ahead of time because of this ensemble tree learning algorithm we've got deployed in production that will show us attacks as they're about to happen. That second case study I find really interesting because it shows the application of a machine learning model from one domain taken completely to something that you wouldn't expect it be taken to. The problem statement here is PowerShell malicious command lines. PowerShell's become the tool of choice for attackers now against Windows. It's got a lot of benefits. It's built into every single Windows installation. It's easy to master. It's very powerful and rich. It can attack without dropping any files on disk, so it can carry out memory-borne attacks that can evade antivirus, traditional antivirus or file filters. And it also allows for very complicated command lines where a human looking at the command line of a PowerShell script has no idea what that PowerShell script is doing. So attackers can hide malicious command lines and make them very difficult to detect that they're malicious. We had applied an n-gram machine learning model in our Windows Defender Advanced Threat Protection to detect malicious PowerShell command lines. And that previous model had a true positive rate of about 89%, which is a pretty decent rate of true positives. Again, we're never satisfied until we get as close to 100% as possible. And so we kept on exploring other approaches to determine whether PowerShell scripts were malicious or not. Our hypothesis is that we could use deep learning to train a model to identify malicious PowerShell command lines, rather than have the traditional n-gram model that would go try to parse and figure out the patterns of the different letter sequences in a PowerShell command line. And so the solution that we came up with was collecting large sets of PowerShell command lines, labeled data sets of ones we knew were malicious, and then use our deep learning toolkit, CNTK, cognitive toolkit, to train a model, a deep learning model, to identify malicious PowerShell command lines. So if you take a look at just how obfuscated a command line can be, you can see that up above there's a command line that's the common core of a malicious script execution there in plain text. And then you can see the kind of obfuscation that an attacker can apply to that command line to make it impossible to tell what the original command line was there. So there's absolutely no discernible pattern, and the number of variations literally are in the billions for how you can take one of these command lines and obfuscate it, but still have it execute the exact same script. So at this point, I would show you a demo of this in Windows Defender Advanced Threat Protection. Unfortunately, I don't have the configuration here to show you that. But what I would demonstrate is show you going into a virtual machine in Azure that has Windows Defender Advanced Threat Protection installed in it, executing an obfuscated malicious PowerShell command line, and then going into the Windows Defender Advanced Threat Protection console, web console, and having that show up as a suspicious command line. Now, what happens behind the scenes in that demonstration is that the PowerShell script is sent up into Azure into what we call a detonation service, where we run the script in a fresh virtual machine that has a bunch of telemetry systems monitoring what happens inside that virtual machine. We do this with unknown executables, too, as part of Windows Defender, where we don't know if something is malicious or not. It's a new executable. We'll go and detonate it inside of one of these virtual machines and watch what happens. The kinds of information we collect off of that detonation include the hash of the PowerShell command line, the machine that it came from, the timestamp, the command line itself, any IP addresses it talks to, files that are modified, a whole set, any kind of impact, any kind of change or interaction with the environment is data that we collect. So this is the kind of data that we can then take and use for training. And in the case of CNTK, we've been using this machine learning model that CNTK is optimized for across a bunch of different domains in Microsoft. You can see Skype for Business. CNTK is great for machine translation, so this will translate text from one language to another using these models. It's also used for image processing, so detecting images and cleaning them up. You can see here as part of Office 365, part of our receipt reimbursement capability that can take an image of a receipt and then normalize it and then translate that into text. That's also using CNTK underneath the hood, this type of machine learning model. And it's really optimized for this kind of machine translation or object recognition or even face recognition. You can see that what deep learning here represents, if you're not familiar with it, deep learning, because there's a bunch of different layers inside this machine learning network where you take the inputs on the left side, you feed it through a bunch of different transformations, and come out with an output on the right side. And what you do with training is you have label data on the right side, and you say, this is malignant, this is benign, and if the model's off, you backpropagate an error into those different layers and have it correct and optimized to try to get to an optimal solution where, given new data set, it will correctly predict whether it's malicious or benign. You can see one of the interesting characteristics of this machine learning model that nobody really understands is the way that each layer becomes specialized to identify different aspects, in this case of a face, where the layer there, the hidden layer 1, will detect little pieces of the face. The second layer will detect larger parts of the face, like eyes and noses. And then that last layer, then, that'll be the full face. And that's what's used, for example, for face recognition or facial identification. In the case of PowerShell, so you're wondering, how do we take PowerShell command lines and map it into that? What we did was take the PowerShell command line, create a normalized array. So if you imagine facial recognition, there's an image, like a PNG or a JPEG. It's X wide and Y height in terms of pixels. And we create a synthetic image off of the PowerShell command line where each character represents a bit in that image. So it's not really an image. It's kind of, you can think of it as an image of the array of characters. But there's a transform on each character to make it show up as a bit. You can see an example there. And then what we do, you can see there's an unobfuscated command line at the top. What that might look like, it becomes more complicated in the image when it's obfuscated. And then we flow that through that same machine learning algorithm to see what it comes up with, based off of the training that we've given it off of the malicious PowerShell command lines. So we train this model at regular intervals based off of the new label data that we get, about 400 gigabytes per day. That takes about just a few minutes to complete on NVIDIA K80 processors or GPUs in our cloud. We then run the classification multiple times a day based off of the kind of the detonations that we get. That completes within seconds. It has to complete within seconds because we don't want to add significant delay between somebody getting compromised and letting them know that they might have been compromised. And you can see that that previous method with its 89% false positive rate, we rose that true positive rate. We rose the true positive rate using this technique to 95.7%. So a very significant jump in the true positive rate. Again, you got to look at the false positive rate and make sure that doesn't increase as well, in which case you're going to undo some of the benefits. We kept that exactly the same. So the very effective algorithm. And now we don't have to go and come up with new regular expressions for determining whether something's malicious or not. We simply feed the data into the machine learning model, and it figures it out itself. Now, the last example that I've got here is another very fascinating one. It's using neural networking for fuzzing. So fuzz testing is something we do with all of our software that might take untrusted inputs and process it. Of course, there's many examples from the past of compromises being the result of bad parsers, not handling untrusted input well and then causing buffer overflows or use after freeze that allow an attacker to inject code execution into across a boundary that they shouldn't be able to cross and then compromise the system. Fuzz testing's approach is to take that piece of code and then throw it a bunch of random input. And random input that will try to detect places where there's invalid or improper handling of inputs and that could lead to a compromise. And there's three types of testing for fuzzing. There's black box, where you just take this data set input, like if you're trying to fuzz a JPEG viewer, you would take a standard JPEG file and then you would randomly mutate it and feed that into the algorithm and see if it causes a crash or some other behavior it shouldn't have. There's white box testing, where you dynamically analyze the flow of the code as the data goes through the algorithm and try to have the algorithm try to figure out, based off the mutations, how to exercise different code paths through that algorithm, so you make sure you get full coverage of all the paths where data is handled. And then there's gray box fuzzing, where humans come up with heuristics aimed at maximizing code coverage. So this is gray box fuzzing is kind of like on top of white box fuzzing. It's applying human intelligence on top of just the machine intelligence that is looking at data flows and trying to optimize the mutations to get full code coverage of that target piece of code. Now, our hypothesis was that instead of having humans come up with heuristics of saying, hey, we looked at these transformations, we see that by looking at the code flow tree that we don't see a bunch of inputs coming down this path, or this path has a lot of complex processing, so let's try to make mutations heavily favor that path to explore it more deeply, is we could apply machine learning algorithms to go figure that out itself, come up with the heuristics. Which paths are the most rich in terms of complexity, and then which kinds of transformations on those input data sets lead to execution down those paths. So we took something called the AFL fuzzer, which stands for American Fuzzy Lop, which is a type of rabbit. That's fuzzer's named after, and which is commonly used for fuzz testing, automated fuzz testing. And combine that off-the-shelf algorithm, which does mutations based off of its own dynamic analysis of code flows, and enhance it with neural network learned targeted locations in the code flow that based off of mutations that could be reached more effectively. So in effect, taking where humans would be in place for coming up with heuristics and replacing it with the machine learning algorithms to come up with those heuristics to try to find maximal coverage of those code flows. The other places where you use what's called sequence-to-sequence neural architectures. Sequence-to-sequence means you've got variable length input, and that's what we've got here with these data sets coming in here, is Cortana itself in speech recognition and Microsoft Translator itself. With these kinds of inputs, text, speech, variable length input. So the sentences are varying length, the fragments of sentences are varying length, and so you need something that is a sequence-to-sequence machine deep neural network architecture to be able to process these. And we decided, hey, let's take this and apply that algorithm taken from those domains into this one for fuzzing. So the model here is we take the inputs that AFL generates and encode those inputs into a sequence of bytes and train this model with the code coverage output, the code flows, and the hotspots that have been determined based off of the analysis of those AFL inputs on that piece of code, on that code sequence. And the learned function that we're trying to train is to come up with heat maps of where in the inputs, what inputs or pieces of the input data set are most optimal in terms of mutations for exercising complex paths through the target piece of code. I'll show you what that looks like in a second. So the kind of scoring that we come up with is mutation at this location in the file, like the header of the JPEG file, very likely to cause, based off of the varying inputs there, to cause lots of different paths through that control flow. And so the fuzzer should spend some extra time there doing mutations versus other places which aren't going to, where it's not going to learn anything new. So the input, so we want to share with you just one example of where we've applied this and tell you about the results of it. I was talking about JPEG files there a minute ago, but one of the places that we've been applying it and looking at its effectiveness is in what's called the readelf piece of code, which is part of the Linux kernel. It is the parser for the Linux file format. So every Linux binary has information in it that describes here's the code, here's the data, here's the size of these different portions of code, here's the type of binary it is. And so that parser is susceptible to attack if an attacker can get a piece of code, a binary, to be executed by that parser and have it be malformed, can cause a compromise of effectively the Linux operating system and allow them to do things that they shouldn't be able to do. So we collected training data, the mutated files generated by AFL. We took the code coverage bitmaps, and then we trained the model off these things to come up with the heat maps. And then we sampled the resulting set at 1%, and then take the AFL off-the-shelf algorithm and process it by itself, with not using this trained model, and then take it and process it by calling into the machine learning model periodically to guide where it spends time doing mutations. You can take a look here at the heat map produced by one of the iterations, on one of the ELF files sent through the machine learning model here. This is the header of the ELF image format, the particular data file that we fed through the model. And this is what came out of the machine learning algorithm, where there's two spots in that header that look potentially interesting to it based off of the code flows that it sees. Those correspond to the number of entries in the section header table at offset 3 hex 3C, that pink location. And a couple bytes later at offset hex 3E, you can see that's the index of the section header table entry that contains the section names. Mutating those with random values causes the ELF parser to go down different paths and provides a rich set of exploration of the parser itself. So let's go ahead and show the video, because this video is going to show you a 48-hour execution of fuzzing the ELF parser off of a massive data set of ELF binaries, one guided just by AFL's own random mutations, and the other one guided by the machine learning model. So can we run that video? So on the left side is the standard AFL fuzzer. On the right side is the machine learning enhanced one. You can see we're at hour 13, 14. When we get up to about 24 hours, you can see here total paths explored, unique crashes. They're on the right side. The enhanced one starts to detect crashes through its mutations it's making, which are likely to be interesting to go explore and see if those are exploitable by an attacker. At hour 48, which is the end of the run, you can see that the number of paths explored by the machine learning enhanced fuzzer is about 1,000 more, about 10% more than, or 15% more than the unenhanced one. And you can see that there were 62 crashes detected in the right side versus, I think it was 7 on the left side. So very effectiveness proven, and not just effectiveness proven in finding locations that we should go look at. For every one of those inputs that ended up causing a crash, Now we go look at them to see if those are real exploitable vulnerabilities or just crashes that an attacker can't exploit, that might just be denial of service. And we take a look of those 6 crash sites. So there were 62 crashes that were detected in that run. 6 of them are unique, and we classified those using an extension to a debugger, the GDB debugger, that goes and tries to determine if they're exploitable or not. And you can see its result was that 2 are exploitable, 2 it doesn't know if are exploitable, and 2 it said not exploitable, just lead to crash. You can see that one of them actually resulted in a CVE there, was exploitable. The second one also exploitable, that was fixed. All of these were fixed in readelf 2.30. So 2 of those were really exploitable crashes detected by this fuzzer. Enhanced fuzzer, none of those were detected by the unenhanced fuzzer. So a great example of how machine learning is enhancing the fuzzer. Now what we're doing now in production, if you take a look at the readelf model performance, just as a summary here, as our fuzzing service that we already have running up in Azure, it's being enhanced with this machine learning driven fuzzing. The amount of data that we trained in that 48-hour run, or we're in a 48-hour run, you can see 20 gigabytes of data. We query the machine learning model for 50% of the mutations. We query the machine learning model for guidance and give that guidance into the AFL fuzzer. And that's the summary of what you just saw in that video there at the lower left. And then you can see the job results here showing you, hey, the fuzzer service has detected crashes on this readelf binary that you should go take a look at. So that is a look at just some of the ways that we're applying machine learning across cybersecurity. And this specific example that I'm sharing with you this morning is where we're taking machine learning models and learning from one domain and applying them to a completely different one with, I think, some pretty thought-provoking examples there of taking just PowerShell scripts and treating those as images and then using image recognition machine learning algorithms to detect malicious command lines, to taking machine learning, deep learning algorithms and applying it to fuzz testing, to taking decision trees and applying it to malicious network data flows to identify compromised virtual machines. This is just a sample of some of the ways that we're using models from one domain and taking it to another one. Of course, we're using machine learning targeted specific domains across all of our products and services. I've been speaking at RSA conference for the last 3 years about our use of machine learning for cyber defense. Every year I've come up with a bunch of different examples to show the kind of innovative work that we're driving with machine learning and cyber security. And again, I think one of the powerful benefits we get at Microsoft for our customers is the enormous data sets that we have to perform this training on. You can see in this talk, I showed you how we're collecting data off of millions of virtual machines to identify malicious traffic patterns, even seeing attacks before they were discovered. We're also taking the telemetry we get off of the millions, tens of millions, or hundreds of millions of endpoints we have with the Windows Defender on them, also taking that and training and applying that to every place our customers are using these systems. So it's one of the benefits of being a cloud service with many different products and services is this enormous amount of data that we have at our disposal to go and come up and really make effective use of machine learning. So with that, I want to thank you very much for inviting me. It's been an honor to speak to you here at AFCEA conference for the first time, my first time here. I hope you found this talk useful, and if you've got any ideas or you're doing work in machine learning and cybersecurity, we'd love to partner with you and see how we can improve our solutions. Thank you.
Ladies and gentlemen, please welcome Lieutenant General Bob Wood to the stage.
Well, I'd like to, Mark, thank you very much. It strikes me that we're asking our cyber security operators to be conversant in everything that Mark talked about. It shows that this is a profession of its own. It's like listening to a doctor talk about surgical procedures, or it's listening to a pilot talking about the skills that he or she really masters. My nephew commands one of our Army cyber battalions, and to ask him what's new, I kind of get that kind of whiplash in terms of the lexicon, the type problems, and frankly, every profession has its own acronyms. I have certainly gathered fuzzing the ELF parser as one thing that's remarkable. But the technologies are there. It really says the partnership between industry and our military or our government is so vital to understand the front edge of what you're describing. So I'm sorry I missed you at RSA this go-round, but I appreciate you bringing that information here. And for all of you in the audience, you'll stick around for a moment, and as you said, perhaps partner or find some new partners. We're really at this point, let's thank Mark one more time, by the way, for just I feel better about my software just listening to you, knowing the kind of rigor that goes into its protection. We are now, by the way, in lieu of a speaker gift, we make a donation to the Fisher House, which helps our military families at our hospitals and our wounded warriors so tremendously. We'll make that donation in your name. Thank you very much. We're going to move to a networking break at this point, during which you can take a look at the final theater sessions. We commence again in this room at 1 o'clock and feature that fireside chat we've described with the DoD Chief Information Officer Dana Deasy and Brigadier General Kevin Kennedy. They'll be here at 1 o'clock. As a reminder, today's luncheon is your final opportunity to sit with some of our DISA senior leaders. The seating chart is in your app. Symposium will conclude with Meet the Seniors upstairs. We've got a good break to get back on the floor with the theaters and back into our exhibit space to take a look at the solutions you see there. We'll see you back here at 1 o'clock. Again, thank you to Mr. Russinovich and to Microsoft Azure for allowing you to speak to us. Ladies and gentlemen, that concludes this session. Thank you.